Hello everybody, and welcome to Part C of Exercise 8. This is another example of determining the interval of convergence of a power series. Okay, and so we're going to start this off the same way that we did for 8 and B by using the ratio test. So we're taking the limit as n goes to infinity of the absolute value of an plus 1 over an, where an again is just our name for the nth term in our series. All right, so if we fill that in, let's see, an plus 1, that's going to be the term in our series that we get by substituting n plus 1 in for all of our n's. Okay, and we're going to divide that by an, which just looks like n times x minus 2 to the n. All right, can we cancel anything? Well, we have x minus 2's in the top and the bottom, so if we cancel those, we're going to get an extra x minus 2 in the top. Notice that x minus 2 doesn't have any n's in it, so we're free to move the x minus 2 outside as long as we remember that we're taking the absolute value of it. So it's going to come outside as the absolute value of x minus 2. And what's left over inside is just the limit as n goes to infinity of n plus 1 over n. Okay, and you might notice when you look at that limit, it's of the form infinity over infinity, so we can use L'Hopital's rule. And we're just going to get a 1 over 1 out of that. Okay, so the absolute value of x over 2, that turns out to be the value of r. Okay, well again, thinking back to what the ratio test says, it tells us that a series converges if the value of r is less than 1. Okay, so we can determine where this series converges by taking that absolute value of x minus 2 and just setting it less than or equal to 1. Okay, so let's see. Algebraically, that's equivalent to turning this into the following three-sided inequality. So if absolute value of x minus 2 is less than 1, then x minus 2 is between negative 1 and 1. To solve that for x, we can just add through by 2. That's going to turn into, let's see, negative 1 plus 2 on the left is going to give us a 1, is less than x, is less than 1 plus 2 is 3. And so what we know is that this interval, x values between 1 and 3, those are x values for which this series is guaranteed to converge. Let's draw a picture of that interval. Okay, so we can put 1 here and 3 here. And what we know so far is that our series converges on this region of the number line that I'm shading between 1 and 3. Okay, but what's missing are the endpoints at this point. Okay, what about right at x equals 1 and x equals 3? The ratio test doesn't help us to determine whether those endpoints converge, so we need to check those separately. Okay, and we'll do that in the space that's down below here. Okay, and I'm going to start with the right-hand endpoint this time, x equals 3. All right, so if we take 3 and substitute it into our series, okay, I'm looking at the very top of the page now. If we take 3 and substitute it in there, we're going to get n times 3 minus 2 to the n. Okay, and so let's see, what does our series look like if we do that? 3 minus 2 is 1, so we're really looking at n times 1 to the n, but 1 to any power is just 1, so we're really talking about the series n equals 0 to infinity of n. Okay, is that a convergent or a divergent series? Okay, well, you can probably look at that and see that it's divergent. And if you really want to check it, just think about the test for divergence here. If we take the limit as n goes to infinity of n, we get infinity and that's not equal to 0. Okay, and that confirms the divergence that we said above. Divergence by the divergence test. Okay, so we've confirmed that over here at the right-hand endpoint, we have a series that doesn't converge. Okay? What about the left-hand endpoint? Okay, the x equals 1. Let's do that now. Okay, so if we take x equals 1 and plug it into our series, we're going to get 1 minus 2 to the n. Okay, if we do the arithmetic there, that's going to be n times negative 1 to the n. Is that a series that converges or diverges? Okay, well, it's kind of a crazy series. If we write out the terms, you'll notice that you get 0 for the first term, and then minus 1 plus 2 minus 3 plus 4 minus 5, and so on. Okay, and I claim that that series also diverges. Okay, we could think about that using the divergence test. Okay, kind of the same strategy that we use for the other endpoint. Because what happens if you take the limit as n goes to infinity of n times negative 1 to the n? Well, notice that that can't be 0 because of the fact that the sequence of terms, if you just look at the numbers that are coming out of our series and think of them as a listing, they don't approach 0. Okay, so this limit is not equal to 0 because the sequence, negative 1, 2, negative 3, 4, and so on, does not approach 0. In fact, it doesn't approach anything because the signs are alternating and the magnitudes are going off to infinity. And so that confirms that this is divergent up here. Okay, so what we've confirmed then is that at both of these endpoints, 1 and 3, we don't get convergence, and so our interval of convergence is just everything between 1 and 3, not including those endpoints. All right, so let's state that answer. So 1 to 3, open interval on both of them, and there's our answer.